let's get started. In the last class we looked at the complete K-epsilon model constants, like all the 5 constants, how it came about for a standard K-epsilon model. And we also just cursorily took a look of the modeling philosophy behind an RNG K-epsilon model, where one of the constant is computed using ratio of 2 time scales. And then we also saw one equation, example of an one equation eddy viscosity model, right, the Prandtl's model. There are other models as well for this, and as I told, I am not going to every eddy viscosity model I will not discuss, that will be the entire semester, but there are some important eddy viscosity models that you will come across, so I will only deal with that one. And one such one is what is called a K omega model. Okay, so we look at this today. K omega model. All right. So first we will see why do we need a K omega model when we already have, let's say, the standard K epsilon, right? It looks like it's functioning well, and it is at least the standard K epsilon model is very popular, numerically stable. So we will see why do we need another model actually, what. Okay, so this reference for this is Wilcox 1988. This is the article. There is also a book written by him which has a lot of information on K omega based models. So if we going to look at again a turbulent boundary layer, okay, so the same example of a turbulent boundary layer. So we have a wall and then a turbulent boundary layer growing over it. So what are the boundary conditions that are required? So we have the velocities, right, u bar, v bar, w bar, right. So the velocities requires boundary condition both in the this is free stream, if you are going to simulate, let's say, a turbulent boundary layer, and also on the wall boundary conditions, right. So wall boundary conditions, free stream boundary conditions are required. So at, let's say, this is y direction, this is the x, and out of plane is z. So at, let me use another color, at y equal to 0, that is the wall, right. So your u bar, v bar, w bar goes to 0 velocity, that is known, and together with it we are computing in K epsilon model 2 extra parameters, k and epsilon. So what will happen to k at wall, y equal to 0, goes to 0, right. K is made up of correlation of velocities, so velocity goes to 0, its fluctuation will also goes to 0. What will happen to epsilon? Epsilon goes to maximum. Epsilon, exact expression for epsilon is correlation of velocity gradients, dou ei prime by dou xj square. So the gradients are large there, so epsilon becomes maximum. So epsilon goes maximum. Okay, so epsilon becomes maximum on the wall. So we need to know, we cannot define what is maximum, you don't even know, right. So that there is an issue there. It's not an issue, there are solutions for it, but as of now it looks like it's not an easy boundary condition to give, something to give like maximum, epsilon is maximum, I don't know what to that, I'll come to that, what can be done, but at least it is not giving any so far any stability issue. So I'm essentially looking into a numerical stability to see whether any issue occurs here. Okay, so with this, let's consider the model parameters and see their stability, right. So consider K epsilon model or K epsilon model components or K epsilon model behavior. Okay, K epsilon model behavior in the near wall zone, in the near wall zone, close to the wall, and the focus is on stability, not accuracy, right? So focus is on numerical stability. Not accuracy. So let's look at some of the terms. These terms are okay, that are going to 0 is fine. Epsilon becoming maximum, it does not cause any numerical stability issue if you figure it out how to give a boundary condition which can lead to maximum epsilon. But let's look at other components. So we have eddy viscosity that you have to compute first in a K epsilon model, right? So we have eddy viscosity nu t, which is equal to C mu K square by epsilon. So y goes to 0, that means as you approach wall, y goes to 0, your K, as I said, goes to 0 and epsilon goes to maximum. So what will this approach to? 0 only, right? Epsilon goes to maximum. So mu t approaches 0, stable. I am not looking into the accuracy issue here, only looking into whether it's numerically stable. So this is completely fine here, stable here. So now what are the other things that I have to compute? I have to compute K and epsilon to get eddy viscosity. So let's look at the K model equation. K model equation. So I have dou K by dou T plus uj bar dou K by dou xj equal to the diffusion term dou by dou xj of, I have only two diffusions that we modeled, that is viscous and turbulent, mu t by sigma K dou K by dou xj, and then the production rate terms, right? So the so called Pk minus epsilon, right? So here again we look at what happens to these terms as I approach wall, okay? So y goes to 0 again, same thing here, K must go to 0, epsilon going to maximum. So these are gradient terms here, the first, second and the third, right? All these are gradient terms. So it will not cause any numerical stability issue, only gradient terms here. So they are fine. Gradient terms. So this is fine. This will not cause any numerical stability issue. Okay. So let's look at then the Pk and epsilon. So we have now Pk model component, that is the production rate of turbulence kinetic energy. You can write Pk model if you want. Pk is equal to your using Boussinesq we have 2 nu t Sij bar minus 2/3 K delta Ij, Boussinesq closure for Reynolds stresses, followed by your mean strain rate. Again y tends to 0, K tends to 0, epsilon goes to maximum. So nu t already is going to 0 here. So nu t will not cause any problem. Okay. Sij is again gradient term here. This is a gradient term. That will not cause any issue. You can compute the gradient close to the wall, and K goes to 0, right? So the K also going to 0. K goes to 0, nu t goes to 0, no issue. This is again gradient. So these are all fine. So PK model is numerically stable. This is also stable, just like eddy viscosity. So far so good. Now what are the other terms we have? We have epsilon. For epsilon we compute an epsilon model equation. So let's go back and see epsilon model equation, whether that is also giving any numerical stability issues. So I have dou epsilon by dou t plus uj bar dou epsilon by dou xj equal to dou by dou xj of the diffusion rate, which is nu plus nu t by sigma epsilon dou epsilon by dou xj plus p epsilon minus, let's say symbolically I am writing it as epsilon epsilon, but that is not the one, right? So we know what the expression for this actually. So here let's look at now, again same arguments here. These are all gradient terms, this entire part gradient terms, which are all fine. I will get no numerical stability issue from gradient terms. Okay, so we'll see what happens to this p epsilon, how we modeled this. P epsilon is essentially depends on production rate, followed by there was a time scale, right? So p epsilon model is nothing but c epsilon 1 pk epsilon by k. Okay, so now if I just look at this, and of course as I said, y tends to 0, k tends to 0. Okay, epsilon should go to maximum. Now this appears like it is going to give a stability issue, right? P epsilon model, as y tends to 0, k tends to 0 means p epsilon tends to infinity, but it is not. If you implement it like this, yes. Let's expand what is pk, okay, because pk is fine. So let's see what happens to that. So sometimes while writing code you have to be careful how you write it. If you are going to implement in a way where the code will blow up, that is you will get something like divide by a very small value or 0, then your code can blow up. So now if I expand it, I will get the pk, which is 2 nu t sij bar minus 2/3 k delta ij dou ui bar by dou xj followed by epsilon by k, right? So I have here epsilon by k, epsilon by k. So now what is nu t? Nu t is c mu k square by epsilon, right? So if I substitute that here, I get c mu k square by epsilon. All right. So if I have this, then what do I get? 2/3 k delta ij. Yes. So now first term we take it up, which is c epsilon 1 2 c mu k square by epsilon sij bar dou ui bar by dou xj followed by epsilon by k. Now you see epsilon will cancel out, k will cancel out. Now it has a k dependency. So the divide by k, that issue which appeared here, doesn't exist when you substitute the eddy viscosity here, right? So if you implement this form, that divide by 0 error blowing up will not occur in the code. Okay, so you have to be careful when you try to implement the code. And then you have the other term, which is so it is minus C epsilon 1 2/3 K delta ij dou ui bar by dou xj epsilon by K. Okay, this is correct, right? Yes. So here again the K will go out, again the divide by 0 is gone. So I have the second term is 2/3 epsilon delta ij. Epsilon goes maximum, so not a problem. So the conclusion here is that this is numerically stable. So P epsilon model essentially does not give any issues, so it will have only a K dependency part. Okay, so this is stable. So no issues here with the P epsilon also. Even though initially it looks like epsilon by K will cause a problem, upon substituting it doesn't. Okay. Yes. So then what is the problem? There is one more term. Let's see that whether that gives an issue, which is the dissipation rate of turbulence kinetic energy, or the destruction rate of epsilon. So if I look at that, which is what we are calling epsilon, which is not, it's just a dissipation rate term of epsilon. So this is model is C epsilon 2 epsilon by K. Okay. So again y tends to 0, near wall behavior, K goes to 0. Here there is no help, there is no eddy viscosity, you don't have your friendly neighbor eddy viscosity to come and help you here, right? Here this will blow up, right? So this tends to infinity. Numerical issue is there, okay? Numerically unstable. This you don't want it. I'm not even looking into accuracy, as I said. We are only looking into whether any term will cause problem as you approach wall. So this particular term can cause an issue. There are of course solutions for that as well. I'm just telling you what is the modeling argument for the genesis of K omega, right? I mean, somebody has to look at, and so that is a disadvantage in that model, therefore I am proposing this model. Okay, I am proposing no model, I am just explaining to you what is the philosophy. Okay, so now one way of having a solution for this is what is called the K omega model. Okay, this is clear so far. You understand that this sinc term in the epsilon model blows up as y goes to 0. You will get this issue here. Okay, so what we do in the so-called K omega model. The first thing is, in the K omega model, we must define what is omega. So an inverse time scale is defined. So omega is nothing but, there are many ways of doing this omega model. I'm just taking on a more like a modeling philosophy idea, not go with the exact derivation. The exact derivation for this exists in the textbook, Wilcox textbook, or some literature. I'll go ahead with more a modeling philosophy similar to the epsilon transport equation we arrived for the model. Okay, so let omega be equal to epsilon by beta star K. So beta star is a constant, so epsilon by K is essentially giving an inverse time scale. Okay, that is an inverse time scale, turbulent time scale only, epsilon by K. Okay, so with this term, what will happen to all the other part? So first of all, we have to see that this when we define this, the last term in the K epsilon will not cause an issue. That is what we have to figure it out here. So let's go back and see first how to get the K and omega equations. Okay, so The k omega equation I'll come to later. K more or less remains same in any type of k base model, right? We saw it in Prandtl's one equation model also. More or less remains the same, whether it's one equation k or RNG K epsilon also, the k remains the same, just the constants are different. Or you take standard K epsilon or K omega, K is more or less remains unchanged. It's the second equation which is slightly different than the one. Okay. So now let's consider the epsilon model equation that we already looked at, right? So which is dou epsilon by dou t, I'm just rewriting it here, plus uj bar dou epsilon by dou xj equal to dou by dou xj of, you don't have to write this again because I've just wrote it in the previous slide, dou epsilon by dou xj plus c epsilon 1 pk epsilon by k minus c epsilon 2 epsilon square by k. Okay, let's call this equation 1 here now. Beta is a constant, I'll come to that value. Okay, so here beta star is a model constant. All model constants I'll give you at the end. So let's so as I said, omega equation can be derived very differently. I will go ahead in the direction of the way we obtained epsilon model equation. So you recall epsilon model equation, we did not derive anything from first principles there. We just made a numerical argument that epsilon model equation should appear similar to a K model equation, transport equation. Okay, right? Epsilon model equation, the way we obtained the epsilon model equation, the way we obtain epsilon model equation was only numerical, we placed only numerical arguments for our own convenience. I am going to do something similar here. So we already have defined what is omega here, right? So this is our omega, epsilon by beta star k. So I am going to say that I am going to replace here epsilon by beta star k. Mathematically this is incorrect because I cannot go ahead and divide epsilon by beta star k. Beta star is fine, is a constant, but k is a function of time and space. So I cannot push k inside the derivative. Okay, so this is mathematically incorrect. I am just going to use only a numerical argument, that replacing epsilon by beta star k to obtain an omega equation. Okay, so what I am going to do here is that I am going to say divide throughout by beta star k. And set it to omega, that's what we want, right? So this is of course purely numerical argument. Okay, so note that we cannot really divide the equation like this, since k is a function of your time and space. So I cannot simply push turbulence kinetic energy inside the transport equation here. Okay, only a numerical convenience. So if I am going to do this, all I am going to do now is that I get dou by dou t. So instead of epsilon by beta star k. So I'll get epsilon by beta star k here plus uj bar dou by dou xj of epsilon by beta star k. This is equal to, so essentially we are constructing an omega equation similar to the way we obtained epsilon equation, but an actual root exists, okay, that you can go and refer, and then nu plus nu t by sigma epsilon dou by dou xj, again going to replace epsilon by beta star k, plus I have C epsilon 1 pk by k here. Epsilon I am going to replace it by epsilon by beta star k minus C epsilon 2. Only one epsilon is replaced by beta star k, not the two here. For consistency, each term we are dividing by k, right? That we have to remember. So only one term, which is epsilon by beta star k, epsilon by k. But the other epsilon k may also want to have a beta star. Why? That is like a sibling. We have to give fruit to both, otherwise the other one will cry. So I will give a beta star also for that. Okay, going to multiply and divide by beta star for that one, so that both gets to divide by beta star k. So if I do this, what would happen to my equation now? I see that it's dou omega by dou t plus uj bar dou omega by dou xj equal to dou by dou xj of nu plus nu t by sigma omega, okay, sigma omega dou omega by dou xj plus we have C epsilon 1, why C epsilon 1? We will have C omega 1, it's an omega equation, pk by k omega, or omega by k basically, right? We have a ratio of, can write this as omega by k now, instead of epsilon by k we had omega by k here, minus we have C epsilon 2, one of the beta star, and then omega square, right? So instead of having C epsilon 2 times beta star, I am going to call it C omega 2, okay, because it's two different constants. So I'll just call it C omega 2. So this C omega 1. Three model constants has appeared. So the last term, if you compare equation 1 and equation, let's call it 2. So the last term here, this was the issue which was giving a numerical issue, right? As y tends to 0, this last term here blows up. That doesn't happen here for us here, okay? So that is one argument, okay? So because we are essentially not looking here as epsilon or divide by k kind of a thing, it is only a argument. So if at all you want dissipation rate in your data while computing equations using k omega, you can use this formula to reproduce epsilon, but in the equation we are only solving for omega, which is an inverse time scale. We are never going to solve for anything epsilon and look at ratio of that with k and all these things. That is only for you post processing. If you want epsilon to compare with some data, you can use that formula. But together with 1 and 2, 1 is also not correct, because 1 is equation for the K epsilon model. So 2 is its counterpart or an equivalent in the omega model. So we need a K equation in the K omega also, that is also required. So before that we need eddy viscosity. right? So this forms one of the equation here. So omega model equation, we have equation 2. Okay, so now we need what do we need? We need eddy viscosity, right? Eddy viscosity nu t. Dimensionally, again dimensional analysis, you can do it and you get essentially k by omega. Instead of c mu k square by epsilon, we get k by omega here. So this is the formula for eddy viscosity in a k omega model. Okay, that gives you same meter square per second, dimensionally correct. So we have model constants that we have to look at, and then I have